Okay, in this video we're going to show the reverse direction. So let G be a region in C, and let U, V be functions defined on G with continuous partial derivatives. Okay, so U and V will be the real and the imaginary part of our analytic functions. And we just discovered if we have analytic functions, U and V must satisfy the Cauchy-Riemann equations. So here, we assume that U and V satisfy the Cauchy-Riemann equation. Two equations, so equations, Cauchy-Riemann equation. And we're going to show the corresponding analytic, a corresponding function will be analytic. So what is a corresponding function? If f of z defined to be the real part u plus I imaginary part v, f of z is u plus iv, then we will show that f is analytic on G. F is going to be an analytic function on G. All right, so that's our purpose. And once we prove that, we will get if and only if is a necessary and a sufficient condition. All right, so to show it is analytic, we need to show it has a continuous derivative. Because UV, they have continuous partial derivatives. The continuity is not a problem. Well, the problem is the differentiability. How can we come up with the differentiability of f? So let z be x plus iy in G. So we have a point, and because G is region open and connected, so this z is an interior point. So there's a disk. Disk centered at z with radius r is contained in G. This z is here, r is here. This is r. This is z. And what is h? Remember that the derivative depends on h. What is h? H is actually the difference, the change. So this is h, right? So h cannot be, the modulus of h cannot be greater than r. So let h be s plus it in C. H is arbitrary point in C. Then we need h inside the ball centered at the origin with radius r. H is close to 0. Then with this condition, we know that z plus h will be inside the disk BZR. All right. Okay, so now let's see what we are going to show. We are going to try to prove this one has the limit, right? This one has a limit. The limit, we actually already know that if it has a limit, it should be. You can have several more than one way, but it should be more or less get something like this. and plus a small 0 part. Small part, infinitesimal stuff. Okay? So you should get something like this, partial derivatives. So you have the real part, you also have the imaginary part. Correct? You have a real part, you have the imaginary part. Okay, so because of this real imaginary part, they are separated. So we're going to like study the real part and the imaginary part separate. We don't want to study them together. So now let's see the real part first. Let's see the real part. What is the real part? Fz plus h minus fz. The real part will be u of x plus s y plus t minus u of x comma y. Right? This is the real part of the numerator. I leave the denominator later. Okay, then both variable change. That's not easy to control. So we are going to insert u of x comma y plus t and plus u of x comma y plus t minus u of x comma y. Right? So we insert this to separate the x variable and the y variable. Okay, once we separate the x variable and y variable, we consider this t is fixed. Now so far we fix this t, and we also actually fix s. So for the second part, x is fixed, yt, x, y plus t, y. And this is the interval. This gave us an interval from y to y plus t, or from y plus t to y, whatever order. Once you have interval, this function has continuous partial derivative. It is differentiable, continuous. All these stuffs give us the mean value theorem. By the mean value theorem, there is a T1 with T1 ops value less than t, ops value of t, because we don't know t is positive or negative, such that this u of x comma y plus t minus u of x y is equal to the partial derivative with respect to y, x, y plus t1 and then times t times the length, right? So this is the mean value theorem. For the y component, we just consider y, that it is a single variable. Then we have such a mean value theorem. And similarly, we also have mean value theorem for this part, but we keep this y plus t fixed. We will have x plus s, x. Similarly, there is an S1 with S1 ops value is less than the ops value of S, and such that u of x plus s y plus t minus u of x y plus t is equal to u sub x, and then here's x plus s1 y plus t times s. Okay, so we have those two conditions, two mean value theorem results. Two mean value theorem results. Okay. Okay, so you see here you have the partial derivative for y, partial derivative for x. Then let's check what is the difference. So we define phi of s comma t as u x plus s y plus t minus u x y. The original one. You see, the original one is very close to those, the sum of them, right? This is the first one. Well, this is the first one. This is the second one. And this sum is almost ux uy. So minus u sub x, x comma y s, u sub y x comma y t. We want to check the difference. Check difference. And this difference, we have what? Remember, we're going to divide it by h. We're going to divide it by h. H is s plus it. H is s plus it. So phi st over h s plus it. And this difference is a sum of them. Difference is sum of them. So we get x part. X part, we use this. This is a ux, x plus s1, y plus t. U sub x is related to s, right? So this one has coefficient x. S, this one also has coefficient s. We factor out coefficient s. Right? We factor out coefficient s. And for the y part, this is a sum. Remember, this is a sum. So it's going to be this term minus it. Even though here's the difference, here's the sum. Because this part is a sum of them. So plus t. So you have t here. Then it's a u sub y x comma y plus t1 minus u sub y x y s plus it. S plus it. Okay? Now let's see. U sub x, u sub y are continuous. They have continuous partial derivatives. We know they are continuous. And s over s plus it modulus is less than 1. T over s plus it, the modulus, is less than 1, right? And we already know that the S1 ops value is less than S. S1 ops value less than S. T1 ops value is less than ops value of T. So what we get? So we get when H approaches 0. In other words, S plus IT approaches 0. This will imply S1 approaches 0 and T1 approaches 0. S1 will approach 0. T1 will approach 0. Right? So by this, let's check the limit. Limit ST both approaches 0, not such that. ST both approaches 0. Phi ST over S plus IT. Okay, and this one, it is, if we put ups value, let's first put the ups value, it's easy to compute. It's going to be less than or equal to the limit S plus IT approaches 0. This is, a coefficient is less than 1, so we only put the U sub x, x plus S1, y plus t minus U sub x, x, y. And plus, we almost apply the triangle inequality. This coefficient is less than 1. Ups value is less than 1. I use ups value. use of value is easy to negotiate. U sub y x plus y plus t1, I'm sorry, comma, minus u sub y x y. All right, and when s plus it approaches 0, this term approaches 0, and this is continuous function, difference will be 0. This approaches 0, this approaches 0, difference will approach 0. So it's 0. The limit exists and equal to 0. Ops value, we know that the limit the limit of ops value is 0 if and only if the limit itself is 0. Okay, so it doesn't matter if it's real or complex. So because of this, we know that the limit s plus it approaches 0, phi s comma t over s plus it is equal to 0. Is equal to 0. Okay. So this proof highly depend on the mean value theorem. Because by the mean value theorem, you can change the difference to be the derivative times the length. Okay. So that's one situation. And this situation, let's rewrite it. By this analysis, what we have in one condition, we have what? We have u of x plus s, y plus t minus u of x, y. It is equal to, where is it? You see, it is equal to u sub x, x comma y times s plus u sub y x comma y t and plus phi st. Phi st is that 0 part with the limit s plus it approaching 0, phi st over s plus it is equal to 0. Okay, so this is the real part. The real part. This phi is defined to be the difference of them, so of course they equal to it. And u and v, they are symmetric, so similarly we have v of x plus s y plus t minus v of x y is equal to v sub x x comma y s plus v sub y x comma y t and plus another function psi of st with the limit s plus it approaching 0 psi of s comma t over s plus it is equal to 0. You just copy them and name the difference by psi of st. Right? Okay, so after we studied the real and imaginary part separately, let's try to add them together. F of z plus h minus f of z. F of z plus h is u z plus h plus iv z plus h. This is f of z plus h minus u of z plus iv of z over h. U of z plus h is this a u of s plus x plus s y plus t, and you group them. It is equal to u of z plus h minus u of z over h and plus I v of z plus h minus v of z over h, okay? And this one is what? Is exactly what we get. U z plus h minus u z is u x times s plus u y times t and plus phi s t. This numerator, and this part is plus I. It is a vx times s plus vy times t and plus psi of st and over h, totally over h. Let's put them together. Totally over h. So far, we still don't use the Cauchy-Riemann equation, right? We don't have a Cauchy-Riemann equation. What is Cauchy-Riemann equation? Ux is Vy. Uy is negative Vx. Ux is Vy. Uy is negative Vx. Okay, so here, this one. And this one, what says? Vy is Ux. Vy is Ux. So we get Uxs plus It Ux times It. Okay, these two terms, we put them together. There's I, so it's I times T. And the other one, Uy is negative Vx, so minus Vx T. Then there's plus I Vx S. And these two. And the rest of them, we just copy. Phi plus I psi over H. Okay? So it's so we have 6 terms. And let's continue. This is a place we use the Cauchy-Riemann equation. Cauchy-Riemann equation. Okay, now let's try it. Continue. Ux s plus it. S plus it is h. Vx is negative. Negative is plus I square. Vxt plus Ivxs plus phi plus I psi. Okay, so this is a Ux times h over h is just Ux. And I, you factor out I, you will get, and you also factor out Vx. you will get IT plus S over H, and plus, right? You factor out I Vx, you have S. And here is a phi plus I psi over H. And we continue this. This is Ux plus I Vx. Phi over H plus I psi over H. What is this? This is f of z plus h minus f of z over h. H approaches 0. This is constant. It does not depend on h. This part is 0. This part is 0. So the limit h approaching 0, f of z plus h minus f of z over h is equal to u sub x of z plus iv sub x of z. The limit exists. F is differentiable. F is differentiable. F is differentiable. All right? And because ux, vx are both continuously differentiable, right? Ux, vx continuous. So F is analytic. F is analytic. Okay, so we spent a long time to come up with the following theorem. Remember, for the analyticity, we have only one definition. The definition of analyticity is a continuously differentiable function is analytic function. And this is the first equivalent statement. Let u and v be real valued functions defined on a region G. And suppose that u and v have continuous partial derivatives. Derivatives. Okay. Then f from G to C defined by f of z equal to u of z plus iv of z is analytic if and only if u and v satisfy the Cauchy-Riemann equation. Okay, satisfy the Cauchy-Riemann equation. Where did we use the Cauchy-Riemann equation? Just here. We organize this ux, uy, vx, vy part and cancel with the h. In this part, we use the Cauchy-Riemann equation. All right. And we actually already prove it. First part, we discover the Cauchy-Riemann equation. Second part, we use this strategy to show that this linear combination u plus iv is analytic. So, well done. Well done. Okay, now let's see one example. we have u of x comma y to be the natural log of x squared plus y squared 1/2. We define this function on what? On this g equal to complex number but without the origin. Because when x, y both 0, natural log of 0 is undefined. Right? Let's try to verify if this u is a harmonic. So to show u is harmonic, let's compute ux. Ux, well, this is natural log is 1/z, right? And 1/2, you can move it forward. So it's a 1/2, move it forward, natural log 2x, x squared, y squared. Right? The change. So it's a x over x squared plus y squared. And uxx again, uxx is denominator x squared plus y squared minus x times 2x. Square, x squared plus y squared and square. Okay, and it's symmetric. You can check that uyy is going to be x squared minus y squared. So from these two computations, you get uxx plus uyy is equal to 0. Is equal to 0. So u is harmonic. On G. U is harmonic on G. But you can see that this cannot be the real part of an analytic function. Cannot be the real part of an analytic function. Why? Actually, you can see that this u is, if you study a little bit, you will see this u is a natural log of the upper value of r, x squared plus y squared, right? No. It is the real part of the logarithmic function. But the logarithmic function is not defined over this region. You must cut it along the certain line. So, but this one is not defined on the on G, on this set. Right? You have to get the principal branch or whatever other branches. So that's give us the idea why this u cannot be. Is this one? Yeah, it's not. It's not. It's not the real part of an analytic function. Yeah. Okay, so it is not a real part of analytic function, which means there's no partner for this u. U is the real part. You cannot find the imaginary part so that these two functions match together to give an analytic function, right? So because of this example, we come up with a problem. Okay, so suppose G is a region in C and U from G to R is harmonic. Does there exist another harmonic function V from G to R such that F equal to U plus IV is analytic? Is analytic in G. Okay, so this is not a trivial question because here you have analytic harmonic function, but it does not have a analytic counterpart. Right? It does not have analytic counterpart. Actually, this part, it may not be that clear. Let's discuss a little bit. If you see this U is a real part of the logarithmic function, you may ask, maybe this U is a real part of another analytic function. If U is the real part of another analytic function, why we worry about this? Because here, U is a real part of a natural log, because natural log cannot be defined, so there's no imaginary part. That is explanation. But possibly it is a real part of this analytic function. It is also a real part of a different analytic function. But that analytic function could be defined over this domain. Then that's a possibility. So far, it looks it's a possibility. So if U is a real part of another analytic function, let's call it G, called G of Z, then what? Then G of Z minus natural log of Z is analytic. And G of Z minus ln of Z has zero real part, has real part of zero. Zero real part, then the partial derivatives are both zero. Right? The difference has no real part, then the real part, the U part with the partial derivative both zero, and then the imaginary part by the Cauchy-Riemann equation the imaginary part must be constant. Imaginary part must be a constant. Again, you're back to the the natural log function. You're back to the logarithmic function, right? If constant means it's a logarithmic function plus a constant. Logarithmic function cannot be defined over this region. Logarithmic function plus a constant cannot define over this function either. Right? So that's an explanation why this U does not have a counterpart of V, so that U plus IV is analytic. It's simply because of this logarithmic function. Okay, so that's the explanation why U has no counterpart. And if this U has a counterpart, V is called harmonic conjugate. If such, let's back to the question, if such V exists, V is called the harmonic conjugate of U. V is called harmonic conjugate of U. Of course, this is not, V is not unique. If V exists, V is not unique. Why V is not unique? Because U plus IV plus IK is also what? Analytic. Right? You just consider V plus K is also the harmonic conjugate. And by the similar argument, and if V1, V2 are two harmonic conjugate, of U, i.e. U plus IV1, U plus IV2 are both analytic, then V1 minus V2 must be constant. Right? Must be a constant on G. G is connected. Remember, G is connected. So harmonic conjugate is unique up to a constant. We will say that harmonic conjugate is unique up to a constant. Up to a constant. So you can add a constant, but if you ignore that constant, is unique. Okay. Okay, let's stop here, and then in the next video, so this lecture is done. In the next video, we're going to show that how we can solve this problem in certain region, not in all the regions. At least you can see in the region C minus 0, this problem cannot be solved because you do find you do have the harmonic function which has no conjugate, but clearly there are harmonic function which has conjugate. You just let the U to be the X, then V to be the Y, and everything is solved. Okay, so in the general domain or general region, we have no idea how to do it, but in certain special region, we can solve it. Okay, so in the next video, we're going to see a theorem which will tell us how to find harmonic conjugate for certain region. Okay, thank you.